In this video, I want to do two more Coulomb's law examples. The first one is the problem that says the real electric attraction between people. It's kind of cute. All right. It says an average human weighs about 650 newtons. If each of two average humans could carry 1 coulomb of excess charge on their person, one positive and one negative, how far apart would they have to be for the electric attraction between them to equal 650 newtons, which is their actual weight? How far do they have to be? If you have just 1 coulomb of charge, how far do you have to be such that the attraction between you and that other person would actually be as strong as how much you actually weigh? It's an interesting question. Let's take a look at it. So we have person 1 and person 2. Okay? And they each weigh 650 newtons. And they each have 1 coulomb of charge. But we don't know how far away they are. We just know that at that distance apart, they're going to feel an electric attraction equal to their weight. Where do we start? Obviously, we just start with Coulomb's law, people. So we have F equals K Q1 Q2 over R squared. All right. In this equation, right, we are actually looking for R, how far apart they need to be. So that's what we're solving for. I'm just going to switch these, do a little switcheroo. So R squared equals K Q1 Q2 over F, right? Well, we know that R then is going to be the square root of K, which is 9 times 10 to the 9, Q1, which is 1 coulomb, Q2, which is 1 coulomb, all over the force between them, which has to be equal to the weight. Piece of cake. We know that that's just going to be 650. And if we put this into our calculator, take the square root, solve for R, I get a value of 3,721 meters. In other words, 3.7 kilometers. All right. This is a fun question. I love this question. It says that if two people are just carrying a coulomb of charge each, okay, they can be 3.7 kilometers apart and still feel a force of attraction between them equal to their weight. In other words, they would feel every bit as strong as gravity 3 kilometers away. So we're talking, between my place in PB and almost all the way to campus, okay? It's a little bit longer, but you get the idea. We're talking if me and someone I knew both had a 1 coulomb bag of charge, we would be attracted equal to the force of gravity. That's crazy and nuts, and it shows you actually how weak gravity is compared to some other forces. It's actually not a very strong force. Even though it's the force that keeps the universe together and holds us in place on this planet, it takes pretty astronomical masses to actually feel that force. Okay, so that's the attraction between people. I encourage you to get a bag of coulombs and try this at home. I'm just joking. You can't really get a bag of coulombs like that. All right. The next example is going to haunt some of you, and I apologize for that. And the reason why I say it's going to haunt some people is because it involves vectors. And I know y'all don't love vectors, but we're going to do it anyways, because force is a vector, which means electric force is a vector, and we have to take this into account. So if you could go to the slide that says finding the electric force when vectors are involved. All right, we have a little situation here. We have a 2 nanocoulomb charge here. We have a positive 1 nanocoulomb charge there. And we have a negative 2 nanocoulomb charge there. And this forms like a perfect equilateral triangle where that's 60 degrees, that's 60 degrees, et cetera, et cetera. Okay? All right, so the question is, find the magnitude and direction of the force on the 1 nanocoulomb charge due to the other 2 charges, due to these two. Okay? And in order to find the magnitude, we need to use vectors because force is a vector. So what do I mean by that? Well, let's take a look. What force will this charge feel due to this charge? Well, they're both the same charge, right? They're both positive. So there's going to be repulsion. So that repulsion will be along the same line. So this over here, that's going to be F1, we'll call it. Okay? That's the first force. And what is going to be the force on the 1 nanocoulomb charge as a result of the negative 2 nanocoulomb charge? Well, this one's attractive. This charge will be attracted to the negative 2 nanocoulomb charge. So in this case, we have it going in this direction. Okay? So if we just assume these are just basically coming from the same point, like the center of this. And then we have here, that's the x-axis, and we have over here a y-axis, right? Okay. So one thing we know for sure, right? This and this are corresponding angles. So you have this line that's separating two parallel lines, right? So this also must be 60 degrees. Okay. And this is totally symmetric here. This and this are totally symmetric. So this has to be 60 degrees. I encourage you to prove that to yourself. And if you get stuck, feel free to reach out to me in office hours and I'll show you the geometry. But prove to yourself that this also has to be 60 degrees using the geometry of this triangle. Okay. Now, this force here, we're going to call it F2. Okay. So how do we solve this? Well, we want to find the net force. So sum of the forces, right? And remember, force is a vector, is going to be the F1 vector plus the F2 vector, right? Now remember how we add vectors. This is the part that I said was probably going to haunt you. So we add vectors by saying F1x plus F2x, right, is in the I direction, right? So we want to find the x component of F1 and F2, right? And we know that F1y plus F2y is going to be in the j direction, right? Which is both y components of this. So in other words, we want to find F1y, x, F2x, and then up here will be F1y and F2y. Okay? How do we find components again? So in other words, this whole problem basically comes down to finding F1x, F2x, F1y, F2y. Because if we can find those, we just put it into this equation. All right. F1x is just going to be F1 cosine theta. We know that, right? This is a great review from last semester, by the way. And we know that F1 is going to be k, so that's 9 times 10 to the 9, right? Times Q1, we'll say, so this force is between this charge and this charge. So Q1 is going to be 2 nanocoulombs, so that's 2 times 10 to the minus 9. Okay. This is 1 nanocoulomb, so that's 1 times 10 to the minus 9, all over the distance between them. And the problem says that these are all 1 centimeters, which is equal to 0.01 meters. So I'm going to put 0.01 meters here, right, squared. And that, my friends, is just multiplied then times cosine of 60. Okay? So I'm going to erase these for now so that I have room to finish this one problem. And if I plug all this in and do times cosine of 60, make sure you have your computer or your calculator in degrees, I get a value of, what value do I get? 9 times 10 to the minus 5. Okay. Now, we could finish the rest of this problem by doing the exact same thing for f2x, f1y, and f2y. We could, and you would get the right answer, and that would be fine. But I'm going to show you how you can use the problem like a little bit of physics jujitsu to make life a lot easier for yourself. Okay? Here's one thing we know. We know that Q1 and Q2 have the same value. There's 1 nanocoulomb and 2 nanocoulombs. Granted, this is negative, but we already are taking the negative into account by saying that the vector is pointing this way. Okay? So that means that if I substitute everything in for f2x, okay, I still am going to get 9 times 10 to the 9. I'm still going to get 2 times 10 to the minus 9. I'm still going to get 1 times 10 to the minus 9. And I'm still going to get the same distance between them of 0.01 meters or 1 centimeter. And again, the angle is 60 degrees. I get the same exact thing, okay? Which means if I solve that, I still just get f2x equals 9 times 10 to the minus 5. And by the way, that's newtons. Newtons. Okay? Pretty cool. We know then that this is really just going to be 2f1x, just doubling the f1x that we get. All right. I'm going to pause here to make a very, very important point. Notice I did not put the signs in for negative 2 nanocoulombs. In the future, I am almost never going to, okay? All you need to do is pay attention to the direction that the sign tells you it has to be. This has to be attracted to that because they're opposite signs. That means the direction of the force is that way. That means that the x component's that way. So if I just add these together, I've already taken into account that sign, right? Leave the signs out of the problem. Only worry about what the signs mean in terms of where the vector should point. You'll get a sense of this, get a hang of it as we do more problems, but you almost never should have to put the negative sign actually into the problem. Always just use the absolute values and have a picture of what's going on so you know whether you should add or subtract. And we're going to see how that works out with the y's in a second. Okay? All right. So that's our f1 and f2x. Now, I am going to tell you, I'm going to prove to you that we don't even have to calculate the f1y and the f2y. Here's why. So we can see here f1y is positive, f2y is negative. Okay? If those two are equal, like f1x and f2x, they're just going to cancel out. And that's exactly what happens. Once again, the only thing that changes here is that f1y equals now f1 sine theta, right? And f2y is going to be f2 sine theta, right? Again, f1 and f2 are exactly the same. We just put 2 times 10 to the minus 9 and 1 times 10 to the minus 9 nanocoulombs. Okay? These have the same value. They're just opposite directions, which means they cancel out and become 0. That makes life so much easier, doesn't it? All right, let's not even worry about it. This will happen in some problems. Try to notice it when it does, when you can actually just make life easier for yourself. So what does this all mean? It all means that my sum of forces, right, is really just 2f1x I, which is going to be 2 times, what do we get again? We got 9 times 10 to the minus 5 I. So that means our sum of forces is just going to be equal to 1.8 times 10 to the minus 4 newtons. That, my friends, is the magnitude. We don't have to do any cool vector stuff to find the magnitude because it's only pointing in the x direction. You don't have to use any Pythagorean theorem. If there was a j direction as well, you would have to use Pythagorean theorem to find the magnitude, but you don't have to do that here. This is the simple answer. That was the first part. The second part was, what's the direction? Well, you're just adding 2 things in the x direction. The direction's just in x, right? The direction's I. So, piece of cake. Piece of cake. You might be yelling at me for saying that it's a piece of cake, and I'm sorry for that. do this problem again, look at it, slow down, go through it step by step. If you want to prove to yourself that these actually cancel by solving for f1x, f2x, f1y, and f2y, you can totally do that, but you will get the same answer of 1.8 times 10 to the minus 4. Whew. And with that, I hope you're feeling like a physics Jedi.